All right, so we're going to start off with number one. So we need to write this expression here using rational exponents. We can see right here it's in radical notation. So remember, when we write this, the base, which is the 7 here, is just going to stay as the base. So we're just going to leave that as a big 7. The 3 that's in the index, that's going to always be the denominator. And then our number that's the exponent stays as the exponent. And that's it. We don't need to calculate this or anything. We just get 7 to the 8/3. Moving on to number 2, we want to solve this equation. So in this case, all of these 6's are the same. So the goal is to eliminate those 6's. So to do that, what we can do is see that we're multiplying here. Multiplication turns into addition. So we're going to add these two exponents up. So 6, 2x over 5 plus x over 3 equals 6 to the 22. And now we can use our rule that if these two if these two bases are the same, we can just set the exponents equal to each other. So 2x over 5 plus x over 3 equals 22. So we'll solve this equation just like we did in Unit 1. We want to get these things to have a common denominator. So in this case, I'm going to pick 15. 5 times 3 is 15. So 2 times 3 would be 6. 3 times 5 gives 15. So 1x times 5 is 5x. So we get 11x over 15 equals 22. So when we add these, we add the numerators, keep the denominators the same. And now we just need to get rid of the 15 and 11. So since I'm dividing by 15, I'm going to multiply by 15. Since I'm multiplying by 11, I'm going to divide by 11. So that's going to get rid of the 15s and the 11s to get y equals, and this would be 2 times 15 for 30. So we get y equals 30. Or x equals 30, sorry. That's an x. All right, that's it. That's what we got. All right, moving on to 3. So we have to solve this equation. Again, we want to get these two numbers to be the same. So right now we have a 4 and a 64. So if we think about how we can get to 64 using powers of 4. So 4 to the first is just 4. And then 4 to the second would be 16. And then 16 times 4, so that's 4 to the third power. So that would be 64. So this is going to be 1/4, still with the 2 plus x, equals 1/4 to the third to the x minus 2 power. So again, we're turning 64 into 4 to the 1/64 into 1/4 cubed, because 1 times 1 times 1 is 1. 4 times 4 times 4 is 64. So now that these two things are the same, we can cancel those out to get 2 plus x equals 3. And power to a power here, I kind of wrote it close to each other, but we are going to turn it into multiplication. And again, this is just a nice little quick equation from Unit 1. So 2 plus x, when we distribute, we get 3x minus 6. We have to get all the x's on one side, so I'm going to minus x on both sides to get 2 equals 2x minus 6. We'll add 6 to both sides to get 8 equals 2x, and then we'll divide both sides by 2 to get 4 equals x. And so that's our value. All right, for 4, it says an exponential function of the form f of x equals b to the x includes the points 236, 3, 216, and 4, 1296. What's the value of b? So to find out what b is, remember b is what we're multiplying by. So if we look, we can see here that 6 times 36 is going to be 216, so the answer is 6. If we aren't sure, again, we can just divide these two. So if we do 216 divided by 36, we're going to get 6, which is the answer. So remember, b is the thing that we're multiplying by, so we just need to find out what we're multiplying by, either by inspection, just seeing, or by calculating with division. All right, for 5, we need to solve this equation. We've got 3 times x to the 1/2 over 3 to the 1/2 power. So in this case, first thing we can see is we've got this x and 1/2. So we can use a power to a power means we're going to multiply. So we get 3x over 2 divided by 3 to the 1/2 equals 3. And now I've got division. So we did our power to a power as a multiply. If we have division, we're allowed to turn that into subtraction. So this is going to become 3 to the x over 2 minus 1/2 equals 3. And I'm going to write this as 3 to the first power. Because I know my goal is I want to get rid of those 3's. So I have to have something up there. We usually don't write the 1, but that is 3 to the first power. I can then eliminate these 3's. So we get x minus x over 2 minus 1 over 2 equals 1. I wanted to already subtract these because they already have a common denominator. So x minus 1 over 2 equals 1. I see division. I can multiply to get rid of division. So this gives me x minus 1 equals 2. Add 1 to both sides. Oops. It is going to be 3, but we get x equals 3. Kind of fun. Kind of interesting that we got another 3, but that's just a coincidence. We're not always going to get whatever number is here, but this time we did. So we had x equals 3. For 6, we need to identify all the key features of 8 to the x power. So the y-intercept, in this case, we'll plug in 0 for x. So 8 to the 0 is equal to 1. So that's our y-intercept. The asymptote, I'm not adding anything or subtracting anything afterwards. So the asymptote is y equals 0. The domain for all the exponentials is always the same. The domain is all real numbers, and the range is the y values. So we're going to go from the asymptote, which is 0, all the way up, because we got 8 to the x, all the way up to infinity. Now this is one that probably would be useful to plot in Desmos if we want. So we got 8 to the x power. So if we do that, we can see that the asymptote of y equals 0. The red kind of lands right on the blue. It's never actually going to touch. There's this dot over here, but we can't actually click it because they never actually touch. And we can see it's going all the way up to infinity. So that's why our range goes all the way out to infinity. The y-intercept right here is at 1. All right. For number 7, graph f of x equals 3 to the x and its asymptote. So a lot of people had trouble with this because they didn't follow the directions. I'm just going to go ahead and put the asymptote down first because I know the asymptote is just going to be right here at at y equals 0. So this is just going to sit right here at y equals 0, and I'm even going to move this down a little bit because I think it's a little bit too high. It looks a little bit better. So that's my asymptote. Now I need to graph 3 to the x power. So I need to actually graph it. I can't just guess. So if I try out some numbers, 3 to the 0 is going to be 1. So I need to plot the point 0, 1. So this is counting by 3's. So 0, 1 would be down here. 3 to the first is 3. So I need to plot 1 for x. I got 3 as my answer. It's going to be right there. I'm not going to draw a straight line because it's a exponential function. So then we're going to do 3 to the second is 9. So 2, 6, 9. So that's that point, 2, 9. 3 to the third is 27. So I'd want to plot 327. But this is 21. So now I'm kind of all the way up here off the graph. So we can see how big it gets really quickly. And I can draw my curve in from there. I feel confident enough to just put my curve in because I'm going to go down, curve it around, and I'm going to lay right on that dashed line, but not actually go past that dashed line. So that's going to be my graph. Again, it's very easy if we want to throw it into the calculator as well. So this time instead of 8 to the x, we have 3 to the x. And we can see we do get that curve. If I wanted to get the table, I can just hit the little table button and get all the values. There's the 139. If I want to come down here and type 3 in, I'll get the 27. They even gave me a couple of negative numbers. If I wanted to be a little bit more specific, this would be at -1, 1/3, and then -2, 1/9, or as they had all the decimals over here, 0.3 repeating and 0.1 repeating. That's what we got for that one. All right, for 8, write the exponential function for the set of points. So we need to do the exponential function. So our function is y equals a times b to the x power. So a is our value at the start when we're at 0. So we're at 8, so that's pretty quick. B is what we multiply by. So again, by inspection, if you want to say we're just doing times 1.5 every time, we can write down times 1.5. X and y stay as x and y, and we're all done. That's it. So that's all we got. If the 1.5, it was a little tough to see, just remember you can always divide these two, and we'll get 1.5 if we divide those. It's always the last one divided by the second to last one. So that's a really quick way to figure out what b is in case you aren't sure, or in case you just want to double check. For 9, Joel saves $60. He triples the amount he saves each week. Does this represent an exponential function? Yes, and the reason is this word triples. So triples means times 3. So remember, all the exponential functions are multiplying or dividing each time. So this one's kind of like a vocab question, so we had to understand what that vocab word means. Then down here, we have to write the function that models the situation. So again, we've got y equals a times b to the x. And we're going to fill in all the parts. So a is what Joel starts with. So he starts with $60. B is how much we multiply by. Triple means times 3. X and y just stay as x and y. So that's it. We got 9. For 10, population of a town is 4,000. It grows at a rate of 2.5% per year. What's the approximate population in 10 years? So again, we can see that we're growing. So since we know that we're growing, we're going to use the growth formula. So the growth formula is y equals a times 1 plus r. So that's going to be our growth factor to the x power. So if we plug everything in, we get y equals a is the start at 4,000. R is 2.5%, so that's 0.025. Because remember, we can divide by 100 to get the per decimal, 0.025, and we get to the x power. In this case, they tell us that we want to do it for 10 years. So we're going to plug 10 in for x. Now at this point, we're just going to throw this in the calculator. So we get 4,000, 1 plus 0.025 to the power of 10. All right, so that's what we got. So we get an answer, and it's got a lot of decimals, so we want to think about what this means in the context of the problem. And in this context, we've got a number of people. So we want to write our answer as a number of people at the end. So we got 5120 people. There we go. So if you round that up to 5121, that's okay. I would prefer this one just because you don't really have that extra person yet, but either answer would be fine. All right, for 11, we got another equation that we had to remember. It's the interest rate equation. So our interest rate equation is the amount at the end is equal to the principal times 1 plus the rate divided by the number of times we're compounding to the power of the number of times we're compounding and then the time in years. So that's all the pieces that we need for our interest formula. So we got A equals for P. P, our principal, is 3,500. In our parentheses, we got 1 plus, now again, R, we have to change that to 0.033. And then N, we're compounding quarterly. So quarterly means 4 times a year, so N is going to be 4. So we got a 4 right there. And then we have our time in years. So our time down here is 5 years. So we're going to do 4 times 5. And again, this is just when we throw it in the calculator. So there's not really much else to do here. So we'll just throw it in the calculator. 3,500. Let's see, is 1 plus 0.035, I think. 33. Divide by 4 to the power of, and we're going to put the parentheses in there so we're still up top, 4 times 5. We get our final result. So after 5 years, that's how much she's got. Again, we want to think about this in terms of the context of the problem. So all those decimals don't make too much sense. Since it's money, money kind of makes sense in dollars and cents. So we'll do 4125.08. So that's how much money she would have. That's pretty good. So after 5 years, she's made over $600, again, with just an investment. 12, we got a population is decreasing. So these fennec foxes are decreasing. So since we're decreasing, we know we want to use the exponential decay function. So that is a times 1 minus r to the t, or to the x. I'll make that an x. We're going to put the time in there, but to keep it consistent, we'll keep it x. So a is our starting amount. We've got 100,000. R is our rate. We're going down at 12%, so that's 0.12, not 12. We aren't told how many years, so we have to leave this as x. But the thing is, we are given this number over here, this 5,000 or 50,000 number. So we can set 50,000 up on that side. So that's pretty cool. Now, again, we're going to need to solve this probably with a graph because we haven't really seen how to solve it algebraically. So I'm going to come over here and put in y equals 50,000. Because that's the first side of the equation. Second side of the equation is 100,000. And then 1 minus 0.12 to the x power. Now, again, nothing shows up because we see our Fennec Fox over here starts at 100,000. So I'm going to use the little wrench, and I'm going to start up here maybe at 200,000, just so I can see everything pretty well. And I think I already see where they connect. They're going to connect all the way over here. So that's our intersection point. So remember, the calculator can do that. That's pretty good. But our job is we need to interpret this. So we need to figure out what this actually means. So this means is that after 5.42 years, we'd have 50,000 Fennec Foxes. So again, we can answer this whole number of years, maybe after 5. We could say about 5.42 years. Is about when we would hit 50,000. So, about almost 5.5, 5.4, somewhere around there. So that's what we got. For 13, it says there are 30,200 bacteria in the lab dish. Population is decreasing at 3% per day. So again, we want to set this up. Y equals A, this amount at the start. And we're decreasing, so 1 minus R to the x power. So y equals A, our initial amount, is 3,200. 1 minus R, well, 1 minus 0.03. And then we're going to the x power. Okay, so that's our equation. That's our setup. So we're decreasing. It says compare the decrease in the population from days 1 to 3 with the decrease from 4 to 6. So complete the sentence with more quickly, less quickly, or at the same rate. How does the population decrease from 1 to 3 versus 4 to 6? So let's go ahead, let's plot this. 3,200. And then 1 minus 0.03 to the x will be that. So I'm way too far out because, again, here I'm up at the 20,000 Fennec Foxes. So let's get this to about maybe 5,000, maybe 4,000 would be good for this one. So I'm going to change my y-axis again to like 4,000. All right. So that's what my graph looks like. That doesn't really look that nice. Again, if we want, we can kind of mess with our axes a little bit. We can just go 0 to 10. We can go 0 to 100 if we want to really see that curve show up. So there's not really anything that's great for this one, because a good window would actually be a little ambiguous, because this kind of looks like a straight line, even though we know it's not. We know we're going from 1 to 3 and 4 to 6 and x. We can't really see anything that good from 1 to 3 or 4 to 6. So what I'm going to do is I'm going to make the table again. I don't want any of these negative values. I just want to go from 1 to 3 and then from 4 to 6. And so these are the values that I have. So this is what I'm trying to compare, is how far we're changing. So from 1 to 3, I need to find the change from 1 to 3. Okay, all right, that's not too bad. 3,104 minus, we'll call that 2,921. And then I need to find this one also. So 2833 minus 2666. So again, we'll just have to do these subtractions to see which one's faster. So we'll see if 1 to 3 is faster, so if we're losing more, if 4 to 6 is faster, if we're losing more there, or if they're the same. So we just have to do these subtractions. All right, so I'm going to come over here. I'm going to stack them up. I could put them in the calculator, but we'll just stack them up and do it by hand. So 3, we get 10 minus 2 is 8. We get 30 minus 29 is, we got 30. Then we have to take one away. There we go. So we just get 83. All right, so we got 83. Okay, that makes sense, right? 2921 plus 3 is 2924. 2924 plus 80 would give me 3084. No, we were at the first time, 183. Okay. Always good to double check. That makes sense. All right, for the other one then. 2833 minus 2666. So here we got 13 minus 6 is 7. I got a 2, I got to borrow again. So 12 minus 6 is 6. 7 minus 6 is 1. 2 minus 2 is 0. So we get 167. So 1 to 3 is faster because 1 to 3 is bigger, so we're going to pick more quickly. And that's usually the case with decay. So when we have the exponential decay, remember it kind of drops off really quickly at first and then slows down. So, I mean, without doing any work, we probably could have just picked more quickly because we know it's decay. For the opposite, for growth, we know it starts growing and then eventually it's going to shoot up really fast at the end. So if this was the opposite, then we would pick probably less quickly. We'd pick the other one because we'd be increasing really fast. But in this case, there's a quick drop off and then it starts to slowly taper away, as somebody had said in the Desmos activity. All right, for 14, we got a sequence here, so we have to decide if this is a geometric sequence. So to figure it out, we have to do all of the divisions. So 162 divided by 54, that's 3. 16 divided by 5 is 3 with a 1 left over. 12 divided by 4 is 3. So we get 3 for these two. I got to check the next two. 54 divided by 18, that's also 3. Because 3 times 8 is 24 and 3 times 1 is 30. Add those up, we get 54. All right, then I got to check the last set. So that's 18 divided by 6 is 3. So I think we're good. Yes, it is. This would be enough work to show the answer. If you didn't want to do any of this work, though, you can just say, well, we're doing times 3 every time. Because if you can see that we're doing the same multiplication or division every time, it's automatically a geometric sequence. So again, either do all of the calculations or give your justification with some reasoning. All right, for 15, we've got another sequence. We have to get the explicit formula, and then we'll have to get the recursive formula. So let's go for it. So the explicit formula is a sub n equals a sub 1, oops, wrong color. A sub 1 times r, what we're multiplying by, times to the power of n minus 1. So that's our explicit formula. And again, the whole idea here is we're just plugging into the formula. A1 is what we got at the start, 12. R is what we're multiplying by. So in this case, we got to be careful because we're not multiplying by 2. We're dividing by 2. So if we're dividing by 2, if we picked out these two, 1.5 divided by 3 is either 0.5 or 1/2. So we're actually cutting these things in half. So 1/2 every time. So n minus 1. And that's the answer. So again, just be careful. Remember that red number should be only bigger than 1 if it's going up. If it's going to be a growing sequence, if the sequence is decaying, that should be a number between 0 and 1. Then we need to get the recursive formula. Formula there, we have A1 equals some number, so we have to figure out what we're starting at. And our formula is AN is equal to R times A sub n minus 1. Because we're just going to multiply by whatever we had last. So in this case, our final answer is always two equations. Our number that we're picking for A1 is at first. That's going to be 12. And what we're multiplying by is going to be, again, this 1/2 that we have. So we get 1/2 times a sub n minus 1. And again, the answer to that one is two equations, just like we did back in Unit 3 when we did the arithmetic sequences, geometric sequences. We've got the explicit if we just want to plug in right away, and the recursive if we just want to cycle through and eventually get to our answer. All right, 16, we have the explicit formula right here, 37 times parentheses 4.5 to the n minus 1 power. What is the recursive formula for this sequence? Again, we're going to find out the recursive one. That's A1 is equal to the first number. And then A sub n is equal to R, whatever we're multiplying by, times A sub n minus 1. All right, well, A1 in this case equals, well, the first number we have is 37, because that's the number that's out front in the explicit formula. So that's pretty quick. An is going to equal something times A sub n minus 1, and that something is what's in the parentheses, 4.5. And we're done. So kind of cool. Also, it looks like we got kind of the same form here. And here is the answer. So if you kind of forgot that one, again, kind of glance over here. It's got a little guide for you. And then for 17, we kind of get the guide in the other direction. So this is our formula for our recursive formula. A sub n equals 7 times A sub n minus 1. We have an initial value. We need to get the explicit formula, which is A sub n equals A sub 1, parentheses R, to the n minus 1 power. All right, well, this one's probably pretty quick too. A sub n equals A1, they tell us right away. It's just 56. R is what we're multiplying by. Well, it's just 7. And then up here, we just leave it as n minus 1. And that's it. We're already done with that one too. So again, these two give us a little bit of a hint. Again, in case we kind of forgot what our formulas were over here for 15 for A and B, there's a little hint for the explicit. There's a little hint for the recursive, because it just tells you which is which. For 18, we have to find out how this differs from the graph of 2 to the x. We know that plus 8 on the end is just going to go up 8. So we're done. If we want, we can double check it. We'll throw these two in here. So we got 2 to the power of x. Let's go home just so I can see a little bit better. And then 2 to the power of x plus 8. Now I got to be careful, because here I've got this plus 8 is after the 2 to the x. Now again, I don't see it, but that's because I'm at 8. But if we zoom out, yeah, we're going from 1 to 9. So from 1 to 9, we're up 8 spots. All right, for 19, pretty much the same thing. We're just seeing what happens if we've got 2 to the x plus 5. So again, if we're up here, we're either going left or right. In this case, we want to remember that when we're in the parentheses, it's always the opposite of what we think it might be. So plus is usually right. So inside the parentheses, plus is going to move us to the left. And again, we'll just throw that in, 2 to the x plus 5. So again, here I want to get the x plus 5 in the exponent. So I'm going to do parentheses x plus 5. All right, we'll go home. A little bit harder to see this one, but we're at 0, 1. And then if we come over here, where is, and we got -5, 1 right there. So you can see I've moved to the left. I'm going to the left 5 to get to the green curve. So that's my answer. All right, final question here, right? Yep. Final one. All right. Function g is a transformation of f of x equals 2 to the x. So what I'm going to do is instantly just fill out this table, because they gave me a little hint table. And I'm going to figure out what 2 to all of these powers are. So 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. And then 2 to the 4 is 16. So it says, find the transformation g of x made to f of x. All right, so we have to find out how we got g of x from the f of x's. So if I want to do that, what I'm going to do is I'm going to compare my values I've got. So f of x versus g of x. So f of x I found here. So that's 1, 2, 4, 8, 16. G of x I'm given right here. So that's -4, -3, -1, 3, and 11. So here we have to use a little bit of number sense and see what the pattern is to try and get from the f's to the g. So if I want to get from f to g, I'm either going to have to multiply or add or subtract or divide. So if I try multiplying first, 1 times -4 is -4, but 2 times -4 is not -3. So I'm not going to multiply or divide. If I want to add, so I'd have to do 1 plus -5 to get to -4. 2 plus -5 is -3. 4 plus -5 is -1. 8 plus -5 is 3. 16 plus -5 is 11. So I could choose to add -5, so that would be one option. Or if I want, I could also just subtract 5. 16 minus 5 is 11. 8 minus 5 is 3. 4 minus 5 is 1. 2 minus 5 is -3. 1 minus 4 is -4. So to get my transformation, I'm going to just do f of x and then just minus 5 from these numbers. For part B, we have to compare the graphs of these functions and then pick all that apply. So some of them we might not even need to graph. Like this one, they're both exponential, so they need to have the same domain, because the domain of all exponentials is always all real numbers. All right. Well, the other ones, same range? I don't think so. I think this one's going to be 5 lower, so I don't think that's true. Same slope? I mean, that's possible. It looks like they're going to have the same slope because we're changing by 1, and then by 2, and then by 4, but I'll look at the graph to double check. Same y-intercept? I don't think it's that one. Well, I know it's not that one, because here I've got -4 and 1. -4 is not 1, so I can get rid of that. So I'm just going to have to pick between B and C now. So I am going to make the graph. So I got 2 to the x, and then 2 to the x, big minus 5. So I'm going to go ahead and get rid of that, because I want x, and I need the -5 to be down here. All right, so, well, the green one's way down here, and the blue one's here, so the y's are definitely different. I guess I probably kind of got rid of that one also. Yeah, they don't have the same range. That makes sense. We can just knock that out. We should have seen that because this is negative and this is never negative, so that's out. But same slope. So this is the one that's really weird because it doesn't really look like they have the same slope. It looks like this one's a lot steeper than this one. But the reason it looks that way is only just because of the way that we're zoomed. If we were to reframe this one, it actually would look the exact same as this one. So these things are going to have the same slope. Again, that's a really weird one to kind of see. What would we have to do to figure that out? Well, kind of like I said, you're just trying to find out the slope. So we have to use our really old school slope formula of change in y over change in x. So if I did that, which it is going to take a while to do all of them, but if we check delta y over delta x, here I'm changing in x by 1, because I'm going from 0 to 1. And my change in y is also 1. Okay? Is that true over here? Yes, because again, my change in y over change in x, I'm going to get change in y is now going to be 2 minus 1 is 1. 1 minus 0 is 1. So this one checks out. I got to check the next one. So again, if I'm doing delta y over delta x, we've got -1 and 3. That's a difference of 2. 2 minus 1 is still 1. For the other one, I've got 4 minus 2 in my y's. 2 minus 1 is 2 over 1. They're both 2 over 1, so that's good. All right, I got to check the next one. So here I can see I'm going by 4. So I've got 4 over 1. Over here, if I do the calculation, we'll do 8 minus 4 over 3 minus 2. So that's 4 over 1. So that checks out. Those are both good as well. We did these. We'll give these a check mark. And I need one more. Let's pick this guy. All right, so for the last one, we'll double check that out. So we're going here and here. So that would be, my face is in the way. I can move myself. So we got to double check. So we got 11 and 3, so that's 8 over 1. And then for the other one, we've got 16 minus 8 in the y's. And the x's, that's 4 minus 3. We get 8 over 1. Those are all the same. So yeah, kind of a long one to do, but they do all have the same slope because our change in y over change in x is always the same. So that's kind of a fun one. That kind of leads into a little bit of the stuff that we were doing in calculus the other day, actually. We're finding out the slopes of all of our crazy curves. So kind of cool. So that's what we got.